In this video, I'm going to talk about some of my group's recent results focusing on the electrochemical oxidation and detection of small organic molecules. In particular, we focus on using platinum-based nanowire catalysts for these processes. And in this talk, I'm going to talk a little bit about not necessarily the catalyst itself, but the support material that we use for the catalyst. So traditionally, the support material for typical catalysts is a carbon-based material like Vulcan carbon, Ketjen carbon. However, these traditional support materials tend to be inactive toward the electrochemical process itself. What we wanted to look at was how can we influence the oxidation mechanism by using a more active support like ruthenium oxide, which is a metal oxide. And there are several reasons why we chose ruthenium oxide. That's because of its high conductivity and its high proportion of oxygen at the surface relative to other oxides. And we wanted to see how this would affect the mechanism of oxidation. So the focus of this work is on looking at how we can use these catalysts to detect small organic molecules. So platinum is a great catalyst, and it can oxidize a wide range of targets: alcohols, glucose, amino acids. But the problem is if you have a good catalyst that can oxidize a wide range of molecules, the question becomes, if you want to have this be a selective catalyst or a selective detector, meaning it only oxidizes one thing, how do you do that? How can you develop a catalyst that normally oxidizes a broad range of molecules, but you've kind of toned that activity down to make it just active toward one particular functional group or one particular type of molecule? And the way that we've been looking at this is by tuning surface structure and composition. In one example would be of alloy nanostructures, and in other examples of tuning the interaction between the catalyst and its support to offer new opportunities to tailor the active sites for SOM oxidation. So in essence, we're kind of constructing platinum sites that are at the surface that are specific to certain substrates. So the reason why we focus on nanowires is because historically they've been shown to be both more active and more stable than other morphologies in terms of catalysis. And this has to do with the fact that they tend to display highly active smooth crystal planes, along with having improved transport characteristics. So that can lead to more efficient transport of electrons. And also they tend to have fewer defect sites, and they tend to be less susceptible to Oswald ripening and other ripening processes that lead them to be both more active and more stable in the long run for the oxidation of SOMs. Now, historically, these catalysts have been primarily tested for their performance in polymer electrolyte membrane fuel cells, and they're active toward both the anode and the cathode, making them somewhat multifunctional toward the oxidation in the anode and toward the reduction of oxygen in the cathode. So that sort of has been the literature precedent for looking at nanowires as these catalysts. And we're kind of more interested, though, in branching out from the traditional fuel cell electrochemistry toward looking at other biological molecule targets and trying to detect them. So, for example, one biological target that you might think of would be glucose. And the reason for this is because of diabetes. So with glucose, the treatment and management of diabetes requires you to, measure your glucose concentration pretty much every day, multiple times a day. And fundamentally, this boils down to an electrochemical process. In essence, you are oxidizing glucose and using the amperometric method, where you compare the oxidation current to the concentration to detect glucose. So this particular process inspires us because we want to be able to look at we want to be able to expand the use of platinum nanoparticles as detectors for biologically relevant molecules like glucose or like other things in the bloodstream. So to introduce you to how we synthesize our ruthenium oxide substrates, what we did was we took a polycarbonate filter membrane, which is something you can buy commercially. It's basically a filter membrane with tubular pores. And we used vacuum filtration to saturate the pores with ruthenium chloride. Basically, we took a solution of ruthenium chloride and we used a vacuum to pull it through and get the ruthenium chloride into the pore itself. Then what we did was we took that template out, dried it, and we polished the outside to remove any residues. This allowed us to get a very high morphological purity of just ruthenium oxide nanowires. Now, what was interesting about the way that we had to do this, normally in these synthetic protocols, the sol gel chemistry is done ex situ, meaning you take your ruthenium chloride solution, you add your gelling agent. In this case, the gelling agent is propylene oxide. So you mix those two chemicals up in a beaker, and then what you vacuum pull through the template is the ruthenium oxide gel. It's already been gelled, and you're just loading the template with the gel. When we tried that using the normal literature protocol, we found that it did not lead to good results. It mostly clumped up on the surface of the template, and it didn't really give us a good nanowire result. We didn't get a good morphology from that. So we had to kind of rethink things, and we developed a new process where we took the ruthenium chloride, but as a sol, we loaded the pores with it, and then we developed a new reactor where we could actually take that template and expose the template to propylene oxide vapors. So in essence, we had our sol inside the template, inside the pore, and then we infused the gelling agent as a vapor into the pore, and then caused the sol to gel chemistry to take place in situ inside the template pore. So we formed our hydrous ruthenium oxide gel inside that template pore, and then when we annealed, we got a very, very morphologically pure sample of crystalline ruthenium oxide. So that was something that was a little different, and something that we developed for this particular project, was a new way of gelling the ruthenium oxide directly in the pore. So we have a standard set of characterization techniques we use at Fordham University. One is X-ray diffraction. So when we took the crystalline product out and we did X-ray diffraction, we saw that the material was primarily made of tetragonal ruthenium oxide, which are the peaks that are denoted by these red standards. And then we also saw a little bit of metallic ruthenium, which was probably at the core of the wire. And we suspect that it was at the core because to oxidize the gel, you need a source of atmospheric oxygen. So you need basically oxygen from the air to react with the ruthenium to form ruthenium oxide. So that it makes sense that at the surface we would get ruthenium oxide, and the core, which is isolated from the atmosphere, when that annealed, that may have led to the production of some ruthenium in the absence of the oxygen from the atmosphere. So we also have access to scanning electron microscopy at Fordham, and in this case, we were able to observe that the wires were nice individually isolated nanowires with fairly large lengths and good aspect ratios, and the diameter of the wires were 140 nanometers. And then we went in and we did high-resolution TEM to measure the crystalline structure of the wires. And as expected, because of the sol gel chemistry, we saw that these were polycrystalline, meaning they were composed of multiple interconnected ruthenium oxide nanoparticles. This is pretty typical for sol gel chemistry. It leads to polycrystalline materials. And we could go in and look at the lattice spacings to see that this was consistent with tetragonal RuO2. So the lattice spacings could be indexed to the lattice spacings of ruthenium oxide. So once we did our template-based synthesis and our characterization, we knew that we had our catalyst support. But then the next step is to develop an active catalyst by taking your support and depositing platinum nanoparticles on the surface. So we use a fairly traditional technique, an ambient solution-based method in aqueous conditions, where we took platinic acid, dissolved it in water, and used sodium borohydride as a reducing agent to convert the platinic acid into platinum, and it formed these nice uniform 3 nanometer particles well dispersed over the surface of the ruthenium oxide. And we actually did the same exact protocol on Vulcan carbon as a control, which is the traditional catalyst support. And we got a very similar catalyst distribution and catalyst size. So one of the most important things that we wanted to do was we wanted to look at how does the catalyst support influence or impact the electronic properties of the catalyst itself. And it's known in the literature that catalyst supports, especially metal oxides, can have strong metals to support interactions. They call this the SMSI, the strong metal support interaction effect. And this has been noted with things like gold on titanium dioxide and other catalysts. So when we did XPS, we saw that the ruthenium was in the +4 oxidation state from the ruthenium 3D and 3P peaks in their positions. But what was more interesting was the positions of the platinum 4F peaks. So we took our platinum nanoparticle on carbon catalyst and our platinum nanoparticle on ruthenium oxide catalyst. We took XPS in the platinum 4F region and we compared them. And what we saw was kind of surprising. The catalyst itself, the peaks were essentially overlaid. So there wasn't a dramatic or intense interaction between the two such that the platinum electronic properties were so different that it led to an XPS shift. So the catalysts were actually close enough that in essence XPS could not distinguish the electronic properties of the two catalysts. So then the next phase was to compare these catalysts, the traditional support to the ruthenium oxide support in terms of the electrochemical properties. And we can do this by cyclic voltammetry. So one of the things that you might be worried about using a metal oxide support is low conductivity. Metal oxides tend to be either semiconductors or insulators. One of the reasons why we chose ruthenium oxide was because this tends to be relatively conductive. Of the different metal oxides, it's one of the metallic metal oxides, so it should be relatively conductive. And if you look at these cyclic voltammograms, in addition to the traditional features where we have the hydrogen adsorption region of platinum and the oxide region of platinum, we can compare this intermediate mid-region, which is the capacitive region, and this should tell us a little bit about the conductivity of the catalyst and the effect of the substrate. So what we saw was that even though we were using an oxide, the capacitive regions were pretty similar. So we were not seeing this dramatic capacitive effect from having a metal oxide due to low conductivity. So in essence, the conductivity was pretty similar. Another thing that might be a concern is, do we get the same platinum utilization when we use a different catalyst? And we did ICP-MS to extract out the platinum loadings on both catalysts. ICP-MS is inductively coupled plasma mass spectrometry. And we saw that basically both catalysts gave essentially the same platinum utilization, about 50 meters squared per gram. So we didn't see any deleterious effects from the ruthenium oxide on utilization. What we did see that was interesting was that there was a negative shift in the oxide peak. This tells us that when you have a negative shift in the oxide peak, this tells us that the ruthenium oxide is leading to the platinum becoming slightly more oxophilic, meaning that it's a little bit easier to oxidize the platinum with the ruthenium oxide than with the Vulcan carbon. So this could be a combination of the electronic interaction between the support and the platinum. That's one possible factor. Or it can also be the fact that the support itself leads to the presence of oxide species at the interface, which we could be detecting also in the CV, meaning the physical interaction and the existing oxide species of the ruthenium oxide substrate may also affect the CV itself of the platinum. So an interesting question that we had to ask ourselves was, what about the XPS? The XPS showed that the two peaks were overlaid, yet we see this negative shift in the oxide peak. So what this tells us is that there is an interaction there. The ruthenium oxide is impacting the electrochemical properties of the platinum, but the effect is relatively subtle, and perhaps it's subtle enough that we can't even detect it in XPS, meaning that we're not doing a bulk change of the platinum itself, the platinum nanostructure, but perhaps at the interface we are getting enough of an effect to be able to detect it in the electrochemistry. So many of you are probably already familiar with the mechanism of SOM oxidation, in particular methanol oxidation, but I just want to kind of recap this, given that the audience might be a little bit broader in this format. So I wanted to just explain a little bit about how methanol is oxidized at these surfaces of platinum. So the methanol oxidation reaction leads to carbon dioxide along with 6 protons and 6 electrons, and this tends to happen at 0.1 volts. That's the standard reduction potential for that half reaction. So now what happens with methanol oxidation is it doesn't happen all at once. It happens in a few different steps. And this is really important because the first step is what leads to the biggest problem of methanol oxidation. So at low overpotentials, what you tend to find is that methanol is oxidized to an intermediate carbon monoxide. And this intermediate carbon monoxide adsorbs to the surface and sticks there, meaning it essentially poisons the catalyst surface at low overpotentials. Now, the effective oxidation of CO requires there to be some kind of oxygen species around, meaning there has to be some kind of adsorbed PTO or PTOH species that comes on. If you look at the CV in the oxide region, we start to put those oxide species on. So it's not surprising that we see the oxide onset happen at the same time that we see methanol oxidation onset to be the case. So everything kind of before this line where we don't have any oxide is where we get CO poisoning and a suppressed methanol oxidation wave, meaning we don't really see methanol oxidation. So the CO oxidation requires some kind of oxygen species to be adsorbed, and then we can get effective methanol oxidation catalysis. So part of the reason why we selected the ruthenium oxide support was because this provides oxygen species over the full potential window. In essence, ruthenium oxide is an oxide. And also we get this SMSI effect where we can make platinum slightly more oxophilic, and it oxidizes at a little bit lower potential. So we can bring down this onset potential a little bit closer to the thermodynamic potential. Basically, this run up here is what we call overpotential, meaning excess potential that you would need beyond the thermodynamic potential. So when we compared the methanol oxidation from the ruthenium oxide support to the carbon support, we see that we get this bump in the activity, and we get much higher activity over the entire onset region. In essence, the ruthenium oxide contributes to a much larger MOR activity relative to the carbon support, especially at low overpotentials, which is important because the low overpotential region is what you would want for a fuel cell. Another way of looking at this is we can sort of take our catalyst and send it up to a potential in this onset region, and then look at how this thing oxidizes methanol over a period of time, like 2.5 hours. We call this chronoamperometry. And what we saw was that the current density over the entire oxidation window of 2.5 hours was higher. And you can see this little sawtooth pattern that was happening. And if you looked at the electrode during this 2.5 hour window, you could actually see carbon dioxide bubbles forming. And that's why we got these little sawtooth patterns. As a bubble would kind of pop off, the activity would go back up. So the suppression of the activity here was in part due to the formation of carbon dioxide bubbles. In the other case, we did not see that sawtooth pattern, and we did not see observable carbon dioxide formation with the carbon-supported particles. So again, some of you in the catalyst community may already know what CO stripping is, but I just wanted to introduce it given the potential for a broader audience. So with support effects in the mechanism of SOM oxidation, we wanted to look at how does the ruthenium oxide affect this primary step, which is the removal of CO, the primary poisoning intermediate of methanol oxidation. The way that we can do that is by taking a platinum catalyst. We immerse it in a solution that's saturated with carbon monoxide. So we basically load the surface with CO. Then we transfer that to an electrochemical cell and oxidize the CO off and see where the CO gets oxidized. See at what potential the CO gets oxidized. And so our CO stripping voltammetry showed us that the ruthenium oxide support significantly decreases the potential for CO oxidation. If you look, the peak where the CO comes off is about 100 millivolts to lower potential than that of the carbon species. So this kind of showed us that not only are we getting the SMSI effect, which is that slight shift in the platinum down to by about 41 millivolts, where the platinum gets a little bit more easy to oxidize, but we're going kind of beyond that. To get to 100 millivolts, we must be getting some effect from the oxygen coming from the ruthenium oxide itself, leading to enhanced CO stripping. So in essence, we're making it much easier for platinum to remove that poisoning intermediate. So to kind of conclude, I'd like to thank my main collaborators in this project. First, we have Dr. Alexander Santulli from Manhattan College. His group worked very closely with us on the synthesis. They were the ones that worked on developing this reactor that we came up with collectively. And they worked with us to make the ruthenium oxide nanoparticles and characterize them. And then we also collaborated with New York City College of Technology and Dr. Lucas Stabarek, who brings expertise in the field of electrochemistry, along with our group's electrochemical background. And the main player that worked on this was William Beatrice. He was the student in my group that did most of the electrochemistry. And a bunch of other students have also worked on these electrochemical projects. Brett, Adam, Daniel, Rosario, Catherine, and Nicole all have worked on these electrochemical projects involving the detection and oxidation of small organic molecules, along with several former group members who have now gone on to different things. So with that, I would like to thank you for your attention. And since I can't answer questions as I normally would, feel free to take a look at the paper, which has a little bit more detailed discussion about the mechanism and the electrocatalysis than could be presented in this talk.